Like I said, now. Great. Well, welcome everyone. I'm glad to have everyone here at seminar. We're very excited to host Vikrant remotely. We were hoping to host him in person last spring, and then that didn't happen. So thank you all for joining us over Zoom today. Vikrant is the Stata Family Career Development Professor in the Thayer School of Engineering at Dartmouth College. He received his bachelor's in civil engineering at IIT Bombay and his PhD in transportation systems from MIT. Vikrant has received a number of awards for his research, including a career award from NSF, numerous paper awards. He's also very active in the TSL community at Informs and also in leadership positions just at Informs in general. And he is an associate editor at Transportation Science. He is, in his free time, co-founder of 2 companies, which I thought was really impressive in addition to everything else. And his work is originally has in transportation and logistics in aviation, but has really spanned into many areas, including healthcare and energy. And I think today's talk is going to be a good example of kind of methods and insights from aviation that kind of can be translated more broadly. So with that, I'm looking forward to Vikrant's talk today on location and pricing and the interplay between location and pricing in transportation, scheduling, and facility locations. Welcome.
All right, great. Thank you so much for that introduction, Karen. It's a great pleasure to be here, even though, as I was telling Changhan, it would have been nicer to be in person in Evanston, but who knows when that's going to happen. I've never been to Evanston, so someday we can make that work maybe. So I'm nevertheless excited to be talking to you guys about some of the work that we've been doing in the past few months here at Dartmouth. And there's a long title here, 2-stage location pricing games in transportation, scheduling, and facility location. I'll talk about all those words in there along the way as we go forward. But let me jump in with some acknowledgements first. So this is work supported by NSF grant number 1750587. And the main author of pretty much everything that I'm going to talk about is my former PhD student. I just had to add that word former because he just defended a couple months back. So old slide, but slightly modified. He's now Dr. Reed Harder, and he's been the main author of everything that I'm going to talk about. And the first half of what I'm going to talk about is also co-authored with a visiting PhD student, Yadong Li, who visited our lab last year. So let's jump into the plan for me. And I would like to keep it interactive. So I don't want to, there is a lot more here than we need to fill up an hour. That's not a problem at all, but I would like to really keep it interactive. So I would very much welcome any questions at any point of time. I think we don't have a huge audience here, so we can keep it informal as much as possible. So what I would like to do here in the next several minutes is first, I just want to tell you a little bit about the kinds of things that we do here at Dartmouth College in our research group. So I'll take maybe 2 minutes of your time talking about just like a overview of stuff that we are interested in. And then I want to talk about what I call as motivation, but it's a bit of a separate study from what I'm going to do later in this talk. So specifically, the focus of this second item here is to try to understand why should anybody care about these 2-stage game models? What's such a big deal about them? I will say multiple times along the way that these are fairly complicated models. So the question is, should we even care about this? Should we do any work with these models? So I'm going to motivate that in a fairly long motivation section here, which is kind of a standalone part of this research. And then around halfway time here, I'm hoping to switch gears a bit. And I want to talk about, hopefully, having established the fact that these game models are important and worthy of our time to study and talk about. I want to talk about some of the insights that we have. I would like to focus on the analytical and computational pieces of it. There is also this empirical validation piece, which I do not think I will have any time to get into. I might just quickly run through it in a couple minutes. So the empirical piece is more about so what part of this research. Like, okay, so you have these models and you have analytical and computational results and whatnot. So what? Who should care? Why should anybody care about how can we use them in the real world? So this is the connection to the real world that I will maybe talk about in a minute or so. So specifically, I will claim that You can validate them against real world data and calibrate and then use for forecasting and scenario analysis. So I might show you a couple of slides on that, and then I'll really quickly conclude in a minute or so. So that's the plan. So with that, let's jump in with some research overview. So what we do here in our research group here at Dartmouth College is we do a lot of different things related to network-wide capacity allocation. So the picture that you see here has a bunch of different firms, each making their own decisions and interacting with other firms, and their decisions affect the customers and are affected by the customers' choice behaviors as well. And then on top of all that, you have some sort of central authorities in most systems or regulators that provide regulations, incentives, investments to try to hopefully improve the system. So there is a lot of interactions there. And finally, not to forget about the most important aspect of a lot of decision makings here is that they are made under a lot of uncertainty. So there is uncertainty on the demand side, there is uncertainty on the capacity or supply side of things. So that's a sort of high level abstraction of the things that we care about. Now, specifically, we spent a lot of time in 4 different streams of research. So one stream of research is very optimization heavy, where we focus on optimizing the decisions of individual firms while trying to capture some of these arrows that you see going everywhere, right? So we try to capture these interactions as much as possible in a realistic way. So that's an optimization piece. Many a times you focus on not one firm's, but multiple firms optimization, and that starts becoming a game theoretic model. So you also focus in this second stream on building and solving game theoretic models of multi-firm systems. And that's what today's talk belongs to. It belongs to this second focus of ours. And then once you have a good understanding of how the game theoretic behavior works, then you can try to integrate this into some sort of mechanism design approach where you try to find out what's right for the central authority or the regulators. How can they incentivize the system to do the thing that's better for everybody, hopefully. So that's the mechanism design piece. And then finally, we spent a lot of time talking about, and this is not a mutually exclusive focus, to be honest with you, we spend a lot of time developing data-driven models of firm behavior, especially accounting for uncertainty in availability of capacity. So delays and disruptions to capacity availability have a significant impact on the behavior of the overall system. So we do spend a lot of time talking about or studying these particular effects of uncertainty within the optimization framework as well. So that's a little bit about us. Now let's switch to the topic for today. And I want to start with the motivation. And to start the motivation, I want to make an observation first. And the observation is that in many real world settings, firms locate their services with the word locate in sort of quotes. I'll explain what that means. But the firms often locate their services near the locations of their competitors. And I want to start close to home. So we are here in the area around Dartmouth, and what you see here is a bunch of different gas stations. This is an actual Google Maps picture, and you see that most of them are clustered together. You rarely have a gas station that's all by itself. There is often a competitor nearby. If you look at the dentists in our area, which is on the border between New Hampshire and Vermont, then again, you see very similar behavior. In fact, a more extreme version of that, where apparently all the dentists like to be in that particular intersection. I don't know why. So that's an observation near home. And then there have been papers written about this sort of clustering behavior in a temporal sense as well. So there are these exaggerated titles for obvious reason, where people would say things like, why do all flights leave at 8 a.m.? I mean, that's exaggerating a bit, but the point is that the flights of competing airlines often are located along the time dimension close to each other as well. So this is an observation that we make, and we are far from being the first people. In fact, this is a well-known fact in the literature. There was a researcher named Harold Hotelling who about 91 years ago, not just observed this, but developed a nice theory to explain some of these behaviors. So in particular, in his work 91 years ago, he considered a particular setting with 2 competitors locating 1 store each on a linear sort of city here, a very simplified setup. And he assumed that the customers are uniformly distributed in this city, and the prices are equal for both these stores, and the customers are very simplistic. They just go to the nearby store. They don't care about any other product um, attributes and whatnot. They simply go to the closest store. And under this setting, hoteling was able to demonstrate that the competitors are going to have incentives to stay in the middle of the city. So both the competitors, in this case, there are just two competitors, both of them would locate their only store right in the middle of the city, right next to each other. So that's what people knew 91 years ago. And this has been, there is a lot of work that has happened since then. And people have talked about hoteling in the air, so referring to transportation scheduling and the clustering behavior in that context, etc. So there are a lot of parallels that can be drawn in a spatial location decision analysis and the temporal location decision analysis. So what would happen if we relax some of these assumptions of hoteling's analysis? What if there are more than two competitors? What if there are more than two stores? What if the pricing is not equal? What if the customers are not that simplistic and deterministic? What if they're not uniformly distributed? It turns out that in all those cases, you can get all kinds of findings. You can have all kinds of radically different patterns that would emerge in these situations. For example, in airline scheduling, you see multiple airlines competing on schedules and prices, which means that they decide their locations of the flights as well as the prices for the tickets in very complicated ways. They're not uniformly distributed passengers along the time axis because there are much more complicated set of preferences. There are more than two competitors, more than two flights to be scheduled. So pretty much all the assumptions are off in these real world settings. And not surprisingly, you see very different findings as well. You don't see all the flights being clustered at 8 a.m. in reality, right? You see all kinds of different patterns emerging. Okay, so far I'm just making a bunch of observations and citing 100-year-old research. So question here is, why should we care about this right now, sitting here in 2020? So why should we model this so-called spatio-temporal location competition, as I'm calling it? We believe that this is a very important thing to study because it has significant implications on things like a lot of different stakeholders, and particularly if these decisions are not made correctly, then there is lots of evidence both in news media as well as in scientific literature that talks about the resulting financial losses, resource wastages, customer inconvenience, environmental damages. All kinds of bad things can happen. And these examples are across all kinds of service industries, airlines, ATMs, communication, transit, rail, retail, and all that. So here are some snapshots. For example, this paper talks about crowding in public transport systems. This one talks about gas stations disappearing across Massachusetts. That's a news article. This one is a paper that talks about rail passenger health and safety in Britain. This one talks about retailers going out of business, etc. So these capacity allocation decisions seem to be something important. They seem to cause significant effects, sometimes ill effects, on important performance metrics in the real world systems. So what can we do? We believe that there are two kinds of broad analyses that one can perform. One kind would be developing optimization approaches that can help the firms optimize their own location decisions. And the other kinds of approach would be predictive, where you're trying to help a central authority or regulators trying to fine tune the infrastructure investments, incentives, and regulations to try to optimize the performance of the overall system. So if they know what would happen under different scenarios, how the players will react to it, then they can predict what the right kind of infrastructure investment and incentives and regulations should be. So that's the motivation of focusing, trying to study these kinds of methods. But they're not easy models to deal with because there are some obvious complicating factors. First of all, the decisions of one firm are very much interdependent with the decisions of other firms. That's one kind of complexity. And the other kind of complexity is that the location decisions cannot be separated in space. They cannot be totally isolated from pricing decisions. Pricing plays a very important role when the firms decide their locations. And to make matters worse, prices are much easier to adjust and are very dynamic and decided at a much later point in time in many different industries. This is sometimes called as dynamic pricing, where uh, many industries such as airlines, rental cars, hotels are known to um, use practices such as dynamic pricing and revenue management. They've been doing this for decades, but now many other industries are getting into this as well. For example, you look at some of these articles, they talk about dynamic pricing for online sellers, and then some other sort of idiosyncratic examples like ski areas and zoos and road pricing and so on. So the point is that dynamic pricing is everywhere, whether you like it or not. A good example, of course, the one I'm going to talk about here for a minute is airline scheduling, where airline schedule make their location decisions basically months ahead. They decide when to offer a flight between what airport to what airport. That's decided and frozen way ahead of the actual departure time. And then most of us customers come in and purchase the tickets much later. So this is a good example where the decisions are made in two stages. There's a clear stage of location decision making, followed by a stage of pricing decision making, and both of these are done in under significant effects of competition from other providers of the same services. And then once you have the first stage of location decisions and second of pricing decisions, then we can estimate what the customers are going to do. We can estimate their behavior, which will, customers will decide looking at locations and prices, what kind of product and service to buy. And Hotelling made some fairly simple assumptions in that particular paper, at least. But over the last several decades, people have identified these models called random utility-based discrete choice models, such as a logit model or a probit model, etc. There is a significant literature from folks in planning, pricing, marketing that talks about how these models are really appropriate to be used for modeling customer choice. And there is a lot of work on both empirical and theoretical side saying that these models are very advantageous for various reasons. So those are the models that we want to use. Of course, they are very complicated models, especially when you try to put them inside a two-stage game theoretic framework. So it all starts looking fairly messy. But hope is not lost. People have done lots of work for the last 90 years since hotelling. In fact, there is so many studies that there are not just review papers, but there are meta review papers talking about the review papers. So there's just a ton of literature. And I just want to say that much. I don't want to get into the specifics of any of these studies for now, given the time constraint. But I want to point out that there are broadly studies in competitive facility location areas and competitive transportation scheduling area as well, sometimes paralleling each other. And some of the important themes that people have identified include solution tractability issues. So what people do, given all these complexities, is either they just eliminate some of the complexities, just ignore them for simplicity, or they account for them, but only solve toy models of a tiny scale. A few decades ago, these approaches called continuum approximation approaches came around, and they are pretty promising. What they say is, look, for most real world problems, you don't need to focus on precise locations. You can get away by focusing on sort of densities or frequencies of services. And that still can fetch you a lot of important insights depending on what your goals are. And I'm going to talk about some such ideas in the second half here as well. Also, the other shortcoming is that there are very few studies that actually focus on any empirical validation of any of these things, really. So the gap here is that there isn't really any unified way of looking at this from a theoretical, computational, and empirical standpoint. So what we try to do is to push the envelope a little bit towards some sort of unified structure of these kinds of spatiotemporal two-stage games. Okay, so I want to now start describing the first model, and this is a busy slide. So I want to walk through this step by step. Specifically, this slide talks about a particular situation, a fairly general purpose situation where we are trying to maximize the profit of a single firm. So we have the profit pie of a firm Q, and the location decisions are XQ. Now, for now, I'm assuming that the frequency is fixed. So we're not talking about how many stores should they locate or how many flights should they offer. We're simply interested in deciding where should the actual locations be. So the total frequency is known and fixed. So what is the payoff looking like? So it's revenue minus cost. The revenue is sum across different locations preferred by the customers. We are summing the number of customers corresponding to that location times if the proportion of customers choosing that service. So this is where your multinomial logit model comes in. And of course, this takes into account in purple there, it's the decisions of the competitors. And then you take the number of customers, you multiply with price, and you subtract the cost, the usual, and then you get some sort of function for the profit or payoff of the firms. So this is the kind of setup that I'm going to look at. I'm going to skip a lot of details, but I want to tell you some important things that we learn when we analyze this model. So I'm going to talk about our work in this context with this 2x2, right? So each column is a different kind of pricing situation. The first column is fixed pricing. So the prices are fixed and known ahead of time. Second column is second stage pricing, which means after the decisions are made about location, all firms, in this case just two firms, will make their decisions on the pricing side. And first row focuses on just one firm optimizing its decisions while the other one held constant. Second row focuses on both players optimizing location decisions. So basically an equilibrium there. So let's focus on top left. What happens when you have a fixed pricing setting with one firm optimizing? Here's a picture of that. So if your incumbent is right in the middle, then the blue curve is the payoff function. And it turns out that this is always going to have this kind of shape, and you can prove that the entrance optimal location is also exactly at the center, just like hoteling, right? Hoteling did this for a very simplified customer choice model. We are doing it for this fancier looking multinomial logit model, but the takeaway is the same. What about equilibrium? Let's say both players are allowed to respond one after the other. So I start here and I start arbitrarily here. Let's say player 2 decides to locate somewhere here randomly. Now player 1 decides to locate here because their frequency, their profit is maximized over here. Then player 2 can respond to that. And it turns out player 2 now decides to move from what, 10-ish location to 50-ish location. Then you allow player 1 to respond again. Then you will allow player 2 to respond again, etc. Very quickly, this will converge. And the big takeaway, as you can see here, is that once again, under fixed and equal pricing, the only equilibrium is at the center, just like hoteling. Again, nothing surprising here. We just use a more complex choice model, more realistic choice model, exact same conclusion. So far, so good. What happens here when we involve second stage pricing? Turns out that things are very different. If you look at the incumbent location in the center and the blue curve is the payoff for the entrant, turns out that the optimal location is far from center. This is always true in these cases. And so the best response to a centrally located incumbent is not like hoteling, it's far away from the center. What about equilibrium? Let's say you let it run again and again. Let's say player 2 first chooses to be here, player 1 chooses to be there, player 2 optimizes, player 1 optimizes. You keep doing that a few times. The big takeaway is that eventually both of them move away from the center, no matter where they started from, both move away, and they are very much not like hoteling once again. So the takeaway here is that we have a very different conclusion on the right-hand side here, where both for optimization and for equilibrium, the players locate away from center. And this is already pretty interesting because you now start seeing how this is actually a better situation typically for the customers on an average, because they have an option, right? Everybody on the left side of the picture can go to the nearby store if they want. Everybody here can go to this store if they want. At least they have the option. So as against the hoteling case where everybody's centered here, so all the customers have to go all the way here. So that's, you already start seeing some of the differences between fixed pricing versus second stage pricing. Now I want to expand on those differences in a significant way. So what we did here is there's again a lot of stuff here. So let's not worry about it for now. I'll tell you what we did here. So we did some computational work looking at both fixed pricing as well as second stage pricing, where we looked at not just one store per competitor, but we looked at more than one as well. And we looked at not just uniform distribution of customers, but all kinds of different distributions. And we looked at a whole bunch of different things. We varied everything, basically, so to say. And then we plotted in orange lines the fixed pricing regime. And then in green line, we plotted the second stage pricing, where the firms can decide different prices for different locations if they want. And then the blue is something in the middle. I don't want to talk about it for now. It's an intermediate kind of setting. There is intermediate level of flexibility to the firms. Now, what we find here is something very consistent and very interesting. So first of all, notice that the orange curve, when it comes to customer convenience, the orange curve is below the green curve fairly consistently. The edges don't matter as much because the edges are where you're varying this alpha parameter, which is how important is the location versus price. And so at one extreme, only location matters. At the other extreme, only price matters. So this whole talk is a moot point when only one of those things matter. So let's not focus on the edges, just focus in the middle anywhere. You see that the orange is always below green here, and orange is always above green here. Same story here. Orange is always below green here. Orange is always above green here. And then blue is typically somewhere in the middle. My point is that left column here is customer convenience. And it seems like it's systematically higher when you have your second stage pricing. And profits are systematically lower when you have second stage pricing. So first of all, these are very different fundamentally, first of all. That's one takeaway. And the more interesting takeaway is that more pricing flexibility as you move from fixed pricing to equal but second stage pricing to unequal second stage pricing, you find that as you offer more pricing flexibility to the firms, their profits drop, but customer convenience improves. Isn't that interesting? So that's something that we find over and over again. I want to show you one more little thing before I want to pause for any questions. So one more thing I want to mention is, what if, let's look at a situation where the firm ignores the second stage pricing. Firm says, hey, you know what? I'm not going to complicate my life that much. I'm going to assume that prices are known historically or whatever. I'm going to ignore second stage pricing and I'm going to work under that illusion. So the firms, so again, the same orange is fixed pricing. So the firm assumes that this is going to be their profit. Now, both of these are profits, by the way. Both curves are profit curves. The firms assume that this is their profit, which looks great, which is high profit. But then in reality, it was this green curve because that was the second stage pricing case. They ignored that. They shot for this. In reality, what happened is that in the second stage, they realized, hey, I can still re-optimize my prices. And when they did that, it's the absolute worst case situation for them. So what's now happening is that they are at a profit point, which is even worse than if they had originally accepted the fact that there is second stage pricing going on. So again, my big picture takeaway is that different pricing models result in systematically and significantly different values of firm profits and customer convenience. So I'm saying it's worth listening to me. That's sort of my point here in the talk so far, hopefully. So let me pause here. I'm going to switch gears significantly. So any questions so far? What I want to now do is I want to switch to frequencies and densities. So as I have mentioned before, these are concepts well supported in the continuum approximation literature, as well as a bunch of other literature. So what I now want to say is that, hey, let's maybe accept the fact that second stage pricing is a big deal. And so let's try to focus on models that probably matter more, models around how many services should the firm locate in different parts of their network. So how many transportation vehicles should they operate, or how many stores should they build, or how many gas stations should they build, things like that. So that's the focus. Rather than focusing on the precise location, we are focusing on roughly how many should be in what part of the network. So that's what I want to talk about for now onward, the rest of the talk. So this is horribly complicated. These are game theoretic models that are generally notorious to have really no tractability and really not a lot of empirical support either. If you look at the literature, there are studies that either do not even try to support things empirically, or actually there are studies that say, hey, it's not supported empirically. There are studies, published studies, that talk about how these game models are inconsistent with the real world data. So what can we do? There are some fundamental sort of existential questions here, right? Is there an equilibrium? First of all, because equilibrium seems to make sense, right? Equilibrium means nobody can deviate unilaterally. That has some logic to it. Does that make sense? Is there an equilibrium, first of all? If there is one, is it even unique, or are there just lots of equilibria? And then even if there is an equilibrium, and even if it is unique, do the players know how to get there, or they have to be these infinitely knowledgeable robots that have to just think in a very complex iterative manner? I'm not saying the firms don't, but is there a way to get away from that highly abstract way of thinking about equilibrium? In other words, can the players get to an equilibrium by simply minding their own business? And then can the researchers get to an equilibrium, like me and you, right? Can we find what those equilibria are in a quick computational effort sense? Otherwise, it's not worth my time. I mean, it's too complicated otherwise if I cannot solve them quickly. And then are these equilibria consistent with actual real world decisions? And then finally, my big question is, can we actually use any of this for anything? So I want to talk about some of these questions in the remaining time I have. So what I want to do is I want to talk about developing a two-stage model of frequency price computation. So frequency is decided in stage one, price decided in stage two. Then I want to show analytically for simpler cases that equilibria exist, they are unique, and simple thumb rules of iterative sort of response, minding their own business kind of approach reaches convergence to equilibrium. And then I want to look at more complex cases and then hopefully demonstrate that these same results hold true for the more complex, more realistic models as well. And then I will probably not get to this much, but I would like to show you really quickly how to solve these games efficiently and calibrate to real world data. And then how to use them for forecasting and scenario analysis. I'm pretty sure I will not get there. So that's the plan for the remaining 15, 20 minutes I have. So the first step here is what model we are using. And there's already lots of debate there. There is good amount of agreement that multinomial logit models make sense, but the utility here, if you're familiar with these models, the big question is, what does the utility look like here at the top, the exponent here? And there are two streams of thought, at least two. One talks about the utility being this kind of negative exponential function of frequency, and the other one talks about log of frequency. And so what we said is, let's not worry about deciding a winner here. Let's just go with both. So everything that I'm going to talk about holds for both formulations, which is kind of amazing because this is saying that it's not the specific details of the utility function that matter so much. What really matters in a structural fundamental way is whether we have one-stage decision making or two-stage decision making. So that's sort of my point. And I think this generalization sort of affirms that point in some sense. Now, what do? We get the multinomial logit model to get the market share. The market share goes inside the player profits. So market share times market size, times price, minus cost, etc. So I'm going to give you some notation, but I don't want you to necessarily dig deep into all of them right now. I want to tell you some important takeaways here first. So the big question we ask ourselves is, how do we solve these problems? I mean, Nash equilibrium is a celebrated idea, but it's well known also that for multi-stage games, Nash equilibrium in and by itself is not good enough because there is many ridiculous Nash equilibria out there. So one way to refine Nash equilibrium is this concept of subgame perfect pure strategy Nash equilibrium, which is what we used and has been used by others as well. The idea is that First, you focus on second stage and decide the pricing equilibrium, and then assume that the players know how the second stage will play out for every possible first stage decision. And that in turn allows them to decide their first stage decision, where the second stage essentially gets embedded inside the first stage decision making. That's sort of the abstract idea. But then this is very difficult to solve. And the question is, even if we can solve it, is this reasonable? So we start tackling that question first. So I'm going to focus on a very horribly simplified model. It's a heavily simplified model that I want to first provide some motivation with, and then I will jump into more complex models. So my very simplistic model has two firms, a single market, unlimited capacity, and no outside option for the customers. Hopefully that's self-explanatory. And the first thing I'm going to say is, I'm going to rattle off a few theorems here without going into details too much. But the first theorem that we can prove relatively easily is that the second stage pricing game has a unique Nash equilibrium always. So that's pretty awesome, because now when the players are deciding the first stage location decisions, they know how the second stage will play out. So this supports the credibility and practical tractability of the second stage of the model, at least. Next here, we are saying that each player's payoff, this is a maximization problem, and this payoff function is what is known as submodular. In the context of our game, it simply means that the cross derivative is negative. Now, this is a little esoteric. Why is this important? And by the way, this is a non-trivial proof. This requires us to embed the second stage game into the first stage game. Becomes quite complicated. But nevertheless, a corollary is very important here. A corollary for two-player games is that submodular payoff functions mean that the game can be trivially converted to a supermodular game. And some of you might identify that supermodular games are very useful because they have this nice property that simple iterative dynamics converge to a Nash equilibrium. So now we're making progress. We feel better about these two-stage game models now. Another theorem, and this is even more complex to prove, but we can prove it by embedding the second stage game, is that the first stage optimization payoff function is concave, which means it's a convex optimization problem. So presumably easier to solve. So that's another nice property to have. If this holds for large scale networks, then we can argue that the optimization is easy. There aren't these multiple weird maxima to look at, etc. Now, I want to also make a comment about concavity. Concavity is not a given, by the way. Many people have looked at single stage models of the nature that we looked at, and they have actually concluded to the contrary. They have found that the games are not convex optimized. There are no convex optimizations there. In fact, the games have this weird S, or whatever you want to call it, shape, where there are convex regions, concave regions. So solving large scale problems is a nightmare there. There are studies talking about that. Compare that to our new discovery that in the second stage pricing situation, the first stage game necessarily has concave payoffs. This is much more desirable to somebody who wants to solve these problems. All right, so this is a stylized model, all kinds of cool properties, but is that relevant for the real world? What would happen if we relax these strong assumptions? So we decided to use what I call as semi-exact or semi-analytical approach. So what we are going to do is we are going to approximate the second stage payoffs with polynomial functions. And then I'm going to look at those polynomials and try to see if they are submodular, concave, blah, 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 right? So I'm going to look at now 1-player, 2-player, 3-player. We also have 4-player situations. We will look at outside option. We will look at various capacity. Basically, we will look at everything that I ignored until now. Okay, so pictorially, here's what I'm doing. For every possible decision of player 1 and for every possible decision of player 2, I'm going to calculate the second stage equilibrium, which tells me the prices. I'm going to take that and I'm going to calculate the second stage payoff using that. So still, we have not done anything to solve the first stage game. Now I'm going to take that payoff function and I'm going to fit to it this nice looking polynomial, second order, fourth order, whatever, right? A lot of it is second order. And then I'm going to see, first of all, is this an accurate approximation? If yes, then are we retaining the properties of concavity, submodularity, etc., that are favorable to us being able to solve? Let's find out. So for example, here is a quadratic fit that we can talk about. And then this slide says I looked at all kinds of things. Students looked at all kinds of things, looked at different parameter values for the different aspects of the problem. Okay, so let's talk about an example result. So first of all, I should say that in nearly all cases, barring some extreme examples, the R-square value of the fit, and guys, I'm not fitting like stupid regression. I'm not doing like 2-parameter, 3 data points kind of regression. This is real, right? I mean, we're looking at thousands of data points in many of these cases and trying to fit 10, 20 parameters to it, 5, 10, 20 parameters. So we do get very strong R-square values. So that's a good starting point. It just means that if nothing else, at least polynomial approximations look okay. Here is the more important thing. So as I said, R-squares are large. We look at the important parameter as estimates like beta 5 and beta 3 that tell us whether the game is concave or not, submodular or not. They have the right signs in all these cases, significantly away from zero signs. So we feel comfortable about the concavity submodularity properties. Now I want to show you this very complex looking slide. All this slide is saying is that even in network situations where we are not focused on one market at a time, the same situation, so same findings hold. So here's an example where we have a transportation scheduling kind of context where we have A to B, B to C, and then indirect one-stop kind of A to C itineraries. And here is the optimization model, which starts looking more messy as you get to larger networks. But still, it has this market share, which is given by multinomial logit. And this utility, by the way, is much more complex now because you have to look at one-stop itineraries and whatnot. Point is that regardless of these complexities, we get very similar conclusions. We find that even with these slightly more complex quadratic approximations with all kinds of interaction terms, etc., we still get very high fit values, and concavity and submodularity still hold. Okay, now there's a problem here. So submodularity gave us a simple corollary that led to supermodular games. That's true only for 2-player games. That does not hold for more than 2 players. But then when we try to work with these problems, they still get solved very quickly. So we felt like maybe these games are still very tractable. Can we try to prove that somehow? Maybe the supermodularity is gone. It's out of the window now. So can we do something else? Can we make it mathematically more rigorous? Because the supermodularity no longer holds, that corollary no longer holds. And without going into the details, there is literature out there that we can rely on, and we can prove some very quick extensions of the existing literature, which basically say that if your games are n-player games with quadratic, the new word I'm adding is quadratic because quadratic fits nicely here, quadratic concave submodular payoff functions, which is exactly what we have, and non-negative strategy spaces, then with some added requirements, and this is another requirement, again, without going into the details, my point is that if these conditions hold, then the frequency equilibrium is unique. And it turns out that they hold almost all the time in everything that we've looked at so far. We have done hundreds of experiments and they pretty much always hold, except for extreme parameter values that are not very realistic. Moreover, if these assumptions hold, then best response algorithm also converges to Nash equilibrium once again. So the thing that supermodularity got us, we are still getting it, even for these larger problems. Taken together, what we are saying is that these properties mean that two-stage equilibria are very much credible, which means they may be good depictions of reality. That's what I mean. They are computationally tractable, which is something I care about personally a lot. And then it says that less than perfectly rational players, the players who don't have this hypothetical infinite rationality, if they go about minding their own business, they can still reach these equilibria. Now I come to that part which I don't think I will have much time to go over, but I want to say something super quick, maybe 5 more minutes, and then I'm done. So I want to give you a quick flavor of how one might be able to use everything that I've talked about so far, right? Because at the end of proving a bunch of theorems, I always feel unsatisfied because I feel like, okay, so what? What are we going to do with these theorems, right? That's not particularly useful if we cannot use them for something. So what we decided to do is we looked at airline data because airlines have lots of data available in the real world. And we looked at this network from the western part of United States for several years time period. So we have Alaska, United, US Airways. Remember that was an airline before. And then Southwest. We looked at those airline networks for a period of some 10 years or so, I think 8 years. And we made some changes to our model where we added some practical constraints, some linear constraints like aircraft availability constraints, etc. But essentially, the core structure of our game has not changed much. We solved them using the same old best response dynamic. And even for such a large network, the amazing thing is that our games solve in a tiny fraction of a second because of the excellent properties like concavity, submodularity, and so on. So this means that we get answers very quickly. This also means that we are able to calibrate these models to real world data, which is nice because that involves lots of reruns. So this is the error measure we use, mean absolute percentage error. And then this is just a picture that says we calibrated to real world data by fine tuning some parameters. And we found good fit both in sample as well as out of sample, which is nice. So we can use past data to come up with guesses about future data, forecasts of future data. So what should I talk about here? Yeah, so there are some error numbers here which look okay. Oh, here is something really interesting at the bottom of this slide. So what this is saying is that this is not just a matter of looking at past predicting future. Sometimes the past does not exist. For example, for a market from Portland, Oregon to San Francisco, there was no direct flight in first quarter of 2007. So what if I'm FAA or I'm somebody related to the airline industry and I want to know if the airlines decide to enter the market, what kinds of frequencies will they offer, right? Now, there is no data on this market. So what we did with our calibrated model is we made a prediction, and the actual frequencies here are Alaska has 3.02 flights on average. That's because there is some up and down through the week or through the month. And then our model predicted 3.52 flights per day. United has 6.11. We predicted 7.28. So yeah, we're not exactly spot on, but pretty close. We get a lot of the ordinal relationships right here. This is saying that when you aggregate, your error improves, which is of course true. That's nothing special here. But this is important because FAA has an entire group that focuses on forecasting at the airport level. It's called terminal area forecasting. So we're working with them to try to kind of help out with some of the things they are doing. So we looked at airport level predictive accuracy, and we get pretty good numbers here. So that's promising. Moreover, we are saying that in some airports where from Q1 to Q4, the observed frequency actually increased, we are able to capture that. On the other hand, in some airports where the frequency stayed the same, we are able to capture that as well. So it gives us some confidence that we are doing something meaningful practically. We can do all kinds of aggregations, and we can look out several quarters. We don't have to do it for Q1 and test on Q4. We looked out 7, 8 years, and we found that gradually the error worsens, but within limits, within 2, 3 years ahead, the error is quite reasonable. And if you compare to benchmark in the literature, these are pretty nice error numbers. Lastly, I'm just going to skip this slide, but this is saying that you don't have to only do forecasting using these models. You can also do scenario analysis, such as what would happen to your entire network if certain airports, such as I think SFO and Seattle, what if they had some congestion mitigation measures? Nowadays with COVID, that's not needed, but this would become irrelevant pretty soon again, as soon as they're back to things as before. And so we can look at pricing methods, we can look at quantity-based methods and try to predict how the network will evolve. So this is the piece where you can help the central authorities and regulators understand how to best manage the system and avoid externalities and generally improve the welfare and profits and convenience and so on. All right, I'm done. All I'm going to say is that this quick takeaway here is that my pricing model is really important. Whether it's two-stage versus fixed has completely different implications for the real world and very different incentives. And many existing models assume fixed prices, and that can lead to, especially if the second stage pricing is the actual reality, then it can lead to very, very different decision making and very different implications for the stakeholders. And then the two-stage models are, first of all, behaviorally consistent. And at the same time, they have better analytical properties such as existence, uniqueness, convergence, stability, and they extend to more complicated cases as well. In short, a more realistic model is also more tractable. So that's a nice thing. You don't get that very often. Now, we also looked at some predictions, and they seem to work out fine, at least in the short to medium term time horizon. And I'm going to leave you with this slide with some pictures of some of the other stuff we are up to here in our research group. Thank you. I have not left much time, but I'm happy to take some questions.
So Vikrant, thanks for the talk. I'll talk to you more about this afternoon, but could your models be used by a company to get competitive advantage? Or is it really just predicting how the market's going to work?
Yeah, that's a great question. So one of the things that we want to look at is, if I paraphrase your question into my model setting, I would say the question you can ask is, what if one company uses whatever are the standard way of optimizing their decisions, and the other company uses our presumably better models, then can they lead to better performance? That's something that is definitely something we are looking at. That's part of the longer term goal, but I don't have an answer right now, but that's definitely a thing on the agenda. Yeah.
So Vikrant, I have a question. So you mentioned COVID at the end. With your models, and maybe the case is just too extreme, but can you think about how frequency and maybe pricing would change with extreme drops in demand? And is the market playing out the way you would expect?
Yeah, so we have actually some work going on right now on that front, where we are not particularly focused on COVID, but we are basically focused on this question of what we call as clean slate scheduling, or scheduling from scratch. Basically, when airlines, when they look at their decisions from year to year, they try to play it safe. They try to not make too many changes unless they are forced to. So COVID is a situation where they are forced to make major changes. So we're trying to look at how the second stage, sort of understanding better what happens in the second stage, can play into that. Once again, my answer is similar to the previous question, that I don't have any, well, I have some results, but they're not that exciting at this moment because they are very preliminary. So maybe in a few months, I will be able to answer your question. On the positive note, I might be able to answer Karen's question sooner than Barry's question. That's also on the agenda, very much so. In fact, my student added a bunch of slides after this, beyond the 72 slides I have, and he said, you should talk about this a little bit. And I said, no, this is not quite ready yet for prime time. So there we are. Cool. Other questions? Changhan, I thought you had your hand raised at some point.
I was clapping.
Oh, okay.
Vikrant, I've got a technical question. I think in the last theorem you showed, you assumed that the equilibrium was unique. Did I catch that correctly?
Yes, there was a. Yes, I think I know what slide that is. Yes, I said that if you look at multiplayer games, yeah, here, right? Yeah, this is the one. Yes, in this game, the equilibrium ends up being unique as long as your coefficients follow some of these requisite conditions. This is, by the way, I should add this somewhere. This is a theorem we prove, but this is essentially a simplification of something else in existing literature. This is not a big brand new theorem here.
And then you had a subsequent theorem where it was part of the hypothesis, I think. So like if this, yeah, so assuming it's unique here, and so if those conditions hold, then you've got uniqueness, but the result holds sort of more generally.
So it's sort of, this is, these conditions are required on top of these conditions if you want to be sure about everything working out in your favor, as in existence, uniqueness, and convergence. If you want all of them to work out, then you need all the conditions to hold. So if the equilibrium is not unique, then, and I don't want you to quote me on this, but I think what happens is that in the cases where it is not unique, there is a range of values, and then I think all the equilibria are in that range of values, and then best response converges to that range, and then all bets are off about exactly which equilibrium it gets to. Is what I recall the exact situation being in that case.
Gotcha. Okay, thanks.
Yeah, but the good thing is that these things are actually very consistent with our computational results. All of these conditions hold pretty much all the time. Pretty much all the time is like 99 point something % of the times, unless you look at some very crazy parameter values that are not difficult to defend, basically, for realistic settings. These are good questions. Any other questions?
Well, I have one quick question.
Yeah.
When you mentioned some of the empirical work that has said that second stage pricing, some of the assumptions don't hold, what in particular are they finding that's inconsistent with the analytical results?
Just the frequency levels are totally different. So I'll tell you the first such paper, the most important such paper is Mark Hansen at Berkeley from 1990s. And he said that at some level, the answers are reasonable if you abstract away sufficiently from it. But if you actually want to care about the frequency values, which is what we do care about, then the results are just very different. Like model will predict frequency of 10 and the actual frequency is 2 or something like that. And that's because of this shape of the function that's totally wacky. And so you have all kinds of non-convexities all over the place. And that leads to jumping between different optima, and you're not even approximately right in many of these cases. So yeah, I think that's an important point. We're not trying to predict prices here. We're trying to use prices as a means to an end. We're trying to predict just what I think personally as an important decision, resource allocation decision of, how many flights, how many stores, where should they be located across the network, etc.
And the data, you have better data on frequency than you do on pricing as well, right?
Yes, that is correct. We have pricing data that's aggregated on a OD level, but we don't have, for airlines at least, we don't have time of day pricing data. That's very true as well.
Well, thank you very much. And thank you to everyone who came today, and we can all clap virtually or.
Thank you so much, everyone.